Welcome back to my YouTube channel. Today we have an interesting topic. Before I continue, if you're new here, hit the subscription button to get notified whenever I post important tutorial like this next time. Kindly use the comment section below for questions. Let's look at a device called Wave Trap. What is this device, and why are we interested in it? Then, have you wondered how two substations communicate or share control signals through a transmission lines of high frequency? How does this high frequency signals affect power equipment? Alright, all these questions will be answered by the end of this tutorial. Let's go into details. A wave trap, also known as a line trap, is a device designed to safeguard switchyard equipment from high-frequency carrier signals. It serves as both a filter and protective device, converting high-frequency signals into low-frequency signals, while providing protection against surge voltages. Understanding the role of a line trap is easier if one is familiar with the communication systems utilized in transmission lines. When two electrical substations communicate, it means they exchange information, control signals, or data to coordinate their operations, ensure reliable power transmission, and maintain grid stability. Think of this: when electricity travels along a transmission line, it can pick up various types of signals, including those from communication systems, or from electromagnetic interference. The line trap is designed to block these unwanted signals, while allowing the primary electrical frequency to pass through. In high-voltage electrical power transmission systems, specifically those over 132 kV, the power line carrier communication (PLCC) system is employed for communication between substations. The carrier signals in this system operate within a frequency range of 3 kHz to 800 kHz, while electrical systems function at 50 or 60 Hz. Consequently, when substations communicate using these high-frequency signals, it can lead to damage to switchyard equipment. This is why wave traps or line traps are installed in series with the transmission line. These line traps obstruct high-frequency signals, allowing only the 50 Hz frequency signals to pass through to the switchyard equipment. Additionally, they provide protection against surge voltages. Let's analyze the simple circuit configuration of the line trap system. Essentially, the line trap is constructed as a parallel resonance circuit connected in series. A coupling capacitor is utilized to capture high-frequency signals, while blocking low-frequency ones. Following the coupling capacitor, there is a protective relay mechanism that activates during high-voltage issues, closing the contacts to ground the excess voltage, to protect both the local monitoring unit, LMU, and the PLCC panel. Let's briefly look at the components of the wave trap and see how they contribute to blocking of this high frequency and ensures power quality. 1. Main coil. This external component is constructed with standard aluminum conductors. Its size is determined by the system's current capacity and voltage rating, and larger coils may be divided into two sections, for practical reasons. A cooling duct, made from spacer bars of epoxy resin and fiberglass, is included to dissipate heat and prevent overheating. The main coil provides a low impedance path for standard electricity flow, while a high impedance path pushes high-frequency signals away. This is due to the increased inductive reactance at higher frequencies and decreased reactance at lower frequencies. 2. Coupling capacitor. The function of the coupling capacitor contrasts that of the main coil. It receives high-frequency carrier signals from other substations and blocks low-frequency signals. When signal frequencies are high, the capacitor's reactance decreases, allowing for low impedance. Conversely, low-frequency signals lead to high reactance, resulting in high impedance. 3. Tuning device. This component is employed to adjust the bandwidth and select specific frequency signals. It consists of inductive coils, resistors, and capacitors. The tuning device enables the selection, or fixing of the receiving signal frequency, and is generally connected in parallel with the protective device. Similar to a radio station, it assists in isolating a particular frequency from a broader range of signals. 4. Protective device. This crucial part of the line trap serves to protect the main coil, tuning devices, and other system components from overvoltage or surge voltage conditions. Typically connected in parallel with the main coil and tuning device, it ensures that these components can operate safely without incurring damage, by grounding any high current flow generated by surge voltages through the help of protective relay. But why do we use line traps in transmission lines? Without delaying, we use line traps in transmission lines primarily to the following reasons. 1. Prevent signal interference. They block unwanted communication signals or noise that can interfere with the operation of the transmission line. 2. Protect communication systems. Many transmission lines carry not just power, but also communication signals. Line traps ensure that these communication signals are kept clear and work as intended. 3. Power quality. This measures of how well the electrical power provided to a device or system matches the ideal electrical power required by that device or system. It maintains that power supply has smooth sinusoidal waveform, constant frequency of 50 or 60 Hz, and constant allowable voltage levels. Lastly, enhance system reliability and efficiency. By reducing interference, line traps improve the overall reliability and performance of both the transmission lines and the accompanying communication systems. We have come to the end of the class. If this tutorial is helpful to you, kindly like, share and subscribe to the YouTube channel for upcoming videos. Thanks for watching, bye for now.